Hello everyone. Let us continue the next module problems of module 3. So we have already started with cantilever beams with all the type of loadings, and this is the continuation of this. So the next problem are the type of problems wherein there is a cantilever which is loaded with two different loads. In addition to this, there are two different types of I values. You can see here, this is AB span has 2I and BC span has only I. It means they have different flexural rigidity. So for this type of problem, things are again simple. The only different thing about this problem is wherever you used to draw the M over EI diagram. So these are the bending moment diagram due to different types of loads. The next thing is, you can check this out. In this problem, like for AB span, you have to divide with 2I, and with BC span, you have to divide with single I. That is the only difference. Rest all is simple. Same like the previous problem. Okay, now let us start with the problem. So find slope and deflection at the free end for the given beam. So first, as usual, draw the diagram. Then after this, deflected shape of the beam is so obvious that because at the free end, deflection is more, and at the fixed end, it is 0. So there are two types of loads here. First is a point load, and then there is a UDL. So for this point load, we'll first draw the bending moment diagram for this. That's how it is 100 into 7. So it is 700 kilonewton meter. This is the bending moment. Next thing is for AB span. For AB span, there is only UDL. So it should start from this point only for the UDL. So bending moment, again, right side, all the bending moment and MOREA diagrams are negative because the cantilever right side clockwise is negative. That's how we have shown it below the 0 line. Next, this is a UDL. For UDL, the bending moment is 10 into 4 into 4 by 2. So 10 into 4 is 40. 40 into 2 is 80. So maximum ordinate here is 80 kilonewton meter. Now because it's a UDL, so you have to join this A and B lines, A and B point, with the cubic or parabolic curve. Okay. Now these are the purely bending moment diagram, but we are more interested in the M over ER diagram, because as it is, if you want to find theta C and delta C, if you want to find slope at C and deflection at C, so we are using the two theorems, that is first theorem, Moore's first theorem. It gives the slope or the theta value of the given beam, and Moore's second theorem gives deflection of the given beam at the given point. So now check this out. This is important diagram. So what we have done here is the same diagram we have redrew here. We have shown here. So this is bending moment diagram. It is point load. So same diagram, A, B, C. C is 0 ordinate. A is the maximum ordinate. Now check this out. We have to do it always part by part, one by one. That is, now first let's start always from the right end. That is from the free end. So at C it is 0. Now we have to find these ordinates. You can see these lines. We have to find this ordinate. So now to find out this ordinate, see BC. B has both spans. That is, B has BC also. Point B has AB also. Now there is difference in the I values. So accordingly, you have to divide this properly. Now check this out. So in BC, this is a triangle, right? So only up to this point, if you want to draw and find this ordinate, so it is 100 into 3. So it is 100 into 3. So it is 300. So it is 300 is the bending moment. Divide by EI value. Again, see here, it is only I value. So I'll just take only EI. I'll just write this EI over here. Now the same ordinate, if you see on the left hand side. Now left hand side has 2I because it has 2I here. So the same 300 over EI gets divided by 2. So it's to see to the left side of B, it is 300 over 2EI. So when you simplify that, 300 divided by 2, it is 150 over EI. That's how I've written this here. Now this same line, you can just see this same line has two different ordinates. So to the right side, if you see, it is 300 over EI. To the left side, if you see, it is 150 over EI. Now, this is very important to draw and mark the ordinate because it has two different EI values. Now, EI is it's the flexural rigidity. So after this, here this 300 divided by 2, I've written here 150. Okay, just write this and leave it off. Next, again in this quantity, you can see here. So it is 100 into 7. So it is actually 700. This complete line is 700. But AB span has 2I. So because it has 2I, this 700 I'm going to divide by 2. So 700 divided by 2 is 300. 700 divided by 2 is 350. Okay. So this 350 EI, it will get distributed now. Basically, this complete line is 350. Now, this is 150. Out of 350, we are going to separate this. We already know this value here. Only check this in AB span. So we already have 150 value. Just draw a line here. So 350 minus 150 is 200. So this portion is 200. So basically this line, 350 line, it will be split into two parts. That is, one is 150, the other is 200. So both put together will be 350. So to make things simple, we have split this into three different. That is, one is triangle. This is also second triangle, and third one is rectangle. Okay. So this is the M over EI diagram for only point load. Next thing is we have to do the same process for M, that is M over EI diagram for UDL, because there's a UDL here. So what I'll do here, same thing. We have already shown this diagram. Okay. So in BC span, there is no loading. So we leave it as it is. Then we have to draw this here. Now at B, this is a 0 point. So at A, it is maximum, that is 80. But in AB span, again, it is 2I. So divide this 80 into 2. So it is 80 divided by 2 EI, which is nothing but 40 over EI. Now these are the two important diagrams which we'll be using to find theta C and delta C. Okay, so after this process, once you draw this, next is just using this diagram for simplification. So let's start this one by one. So first thing is we have to find out delta C and theta C. So theta C. So theta C is this portion, deflected portion. You have to find this theta C. So it is nothing but area of a rectangle. Again, now this is your choice. You can name this 1, 2, 3, 4 or 1, 2, 3, 4, provided you consider all the areas of the M over EI diagram. So let's start with this here. First, theta C. Actually, it is theta C here. Okay. So theta C. First, area of a rectangle. This is the area of rectangle. Next, I've shown here. I've shown this markings as 1, 2, 3, 4. So this is second. So area of a triangle. Next, area of third triangle. And finally, area of a parabola. We'll call this parabola because this is a parabolic curve. Okay, so it's always important you mark this 1, 2, 3, and 4 because as there are many areas, so things become simpler if you nomenclature this. So 1, 2, 3, 4. And the same areas, you can use it here. 1, 2, 3, 4, like this. Okay. All right, let's start with this. So if you want to find theta C, it is actually theta C minus theta A. So it is area of M over EI diagram. All right. So because it is M over EI diagram, so 1 over EI is common for all the areas. So you can see here M over EI, this 300 over EI, 150 over EI, here also 150 over EI, and this is 200 over EI. So what you're going to do here is we're going to take this EI common. So 1 over EI is common. So next, after this, first area of a rectangle. So take this rectangle. So area of a rectangle. So area of a rectangle is length into breadth. That's how it is 4 into 150. So this is 4, 150. Similarly, next area of a triangle. Area of a triangle, again 1 over EI common. Next, this triangle, half into base 4, height is 200. Next, third area, area of a triangle, that is half into base 3 meter, height 300 over EI. Okay. Next, 1 over EI common again. Next, now this is the parabola. So area of a parabola, parabolic curve, is 1/3 of x and y. So 1/3, x is 4, y is 440. So when you simplify all of this, so you get 1 over EI, that is 1503.33. Now the answer what you've got, this answer what you've got is positive. So that means it is in the clockwise direction. If the answer you get negative, it is the anti-clockwise direction. And one more thing, and most of you might be getting a doubt, as in because we have drawn this as in the negative side, that means you have to take 150 as minus or 200 as minus. So see, the simple logic is areas can never go minus or they can never be negative. Okay, so this is for us to draw the bending moment or the M over EI diagrams. As it is, once you draw this, just take the areas. Don't consider the signs. The signs are only for the diagrams. So you're supposed to mark the areas as it is, always a positive value. Again, a simple logic, area can never be negative. That's how we are not taking any negative values here. Okay, so once you find out this theta B, next is you have to find delta C. Again, see, finding delta C is also simple because it is nothing but area into CG distance. Area into CG distance. Next, third, area of a triangle into CG distance. Finally, area of a parabola into CG distance. Now, having that, we have already found out the area here. You can see here 600. When I multiply this, this is the area. We have already found out this area. Next quantity, third quantity, and fourth quantity. Now, things become easy if you solve it like this. Now, see here, because they've asked us to find theta C or delta C here, so always we'll measure the distance with respect to C, that is CG distance with respect to C. Now, first moment of area, so delta C is the first moment of area, or it is also called as moment of area of M over EI diagram. Moment of area is nothing but area into its CG distance. So area into its CG distance. Now there are 2 points here. Now they've asked us to find out about C. So that's how we have to find. You have to find complete from A to C about C. You have to always find moment about a given point. So it's C now. So as usual, first thing, it's area, moment. First moment of area is nothing but area into CG distance. So this is area. See, 1 over EI, again, it is the M over EI diagram. You have to take it common. So this is area. Now first, CG distance. Now check this out. CG. So this is the CG distance. So CG of a rectangle is exactly at the center. So 4 divided by 2. So you're at this point now. But they've asked us to find about C. So that's how 4 divided by 2 plus 3 meter. This distance you have to add. Similarly, the next quantity now. So next quantity is a triangle. So area of a triangle, 1 over EI. See again, because you've already found out here, take down this value. Directly you can write it here. Otherwise, again you have to put area, that is half into base into height. Unnecessary, you have to increase all the steps. So things become simpler when you solve it here only. So this is 400 area. Then now area of this here, centroid of a triangle measured from the apex. Now this is a point. From here, if you measure, is apex. So again, why you're measuring like this is because you have to measure with respect to C. From C, it is like this. So first you can meet here is apex. So centroid of a triangle measured from the apex is 2/3 of the base. So 2/3 of 4 meter. So 2/3 of 4. But because you're finding about C, so you have to add +3 for this. So that's how +3. Next, third quantity. So the third quantity is this triangle. Now again, in this triangle, third, we have already found out the area here, 450. So write it here, 1 over EI into 450. Next, CG distance. So it is again from this point. So the first thing what you can come across here is the apex. So apex is 2/3 of the base. So it is 2/3 of 3 meter. So 2/3 of 3 meter. Next, finally, the fourth quantity, that is M over EI. We have already found out this area here into now this distance. So again, the CG of the parabolic curve is 3/4 of x distance. This is 3/4 of this distance. So 3/4 of 4 plus 3, because you're finding the CG distance about C. So +3. So again, if you simplify all of this one by one, so you will get this answer. Again, the answer is positive. So the moment is acting, the deflection is acting downward. Here also answer is positive, slope is acting, that is rotation is clockwise. Okay, the next problem is again the same cantilever problem. This time there are two loads, both are point loads only. Actually, it is not visible here, but at a 4 meter, there's 10 Newton. And for the next 2 meter, there is another load that is also 10 kilonewton. All right. So determine the slope and deflection of the loaded beam by moment area method. Now again in this problem, they have not specifically told you at the free end or any given point. They have neither told find at the free end, nor they have told any specific point. So it is understood that whenever they ask you such type of problem wherein they've just asked you find slope and deflection for the loaded beam. So it is understood that you're supposed to find at two different points. You have to find slope at this point, slope and deflection at this point, also slope and deflection at this point. Okay, so you have to find theta C delta B, theta B delta B. You have to find both the quantities unless and until it is not mentioned. So as usual, we have to again first draw the deflected shape. You can see here, just draw the deflected shape of the beam. Obviously at a fixed support, the deflection and rotation is 0. So this is a straight line. Then this is the deflected shape of the beam. Now you can check this out. See, vertical displacement. This is a vertical displacement. Delta B, delta C. Then exactly at this point, when you draw the curved portion of the beam, exactly at this point, just draw a tangent. That will give you delta B. Similarly, at C, just draw a tangent like this. That is straight line. Then that will give you theta C. So you have to find all the four quantities now. So when you find the four quantities, again things are simple. You have to use the first two theorems to find out theta B and theta C, delta B and delta C. Okay, so let's start with this. First, the bending moment diagram. So we'll just find out here. So first thing is 10. So bending moment at B, this is a B point. Bending moment at B is 0 because it's a free end. Next, bending moment at C. So this is a 10. So 10 kilonewton load. So it is 10 into 2, this distance. So 10 into 2 is 20 kilonewton meter. Similarly, bending moment at A, 10 into 6. Next, plus 10 into 4. So that is bending moment at A is 100 kilonewton meter. So next, our main intention is to draw the M over EI diagram. So it's basically bending moment diagram only, but it just has EI value below it, The denominator will have EI values. Okay, so you can see here first B. Next, at B it is 0, at C it is 20, and at A it is 100. So you can see here B to C 20. You have to just divide it over EI. Now you can see here AB and AC and BC, they have the same EI value. Unless and until it is not mentioned, it is understood that the I is common for both of this. I or EI is common for both of this. So this is 20 over EI. Next, similarly, this is 100. Now you can, what we'll do here is to make things simple. This is 20 and this is 100. You can treat this as trapezoidal also, but remembering the area of a trapezoidal or the CG of a trapezoidal is a little complicated, even the simplification. So to make things simple, what we'll do is, this is 100, this is 20. So I'll just draw the straight line here. Okay, so this is 20, this is also 20. So the rest is 100 minus 20 is 80. So this is 80. So we know the area of triangle, rectangle, triangle. Again, the choice, this marking this numbers is your choice. You can mark anyhow, provided you should mark, simplify and identify all the areas and consider all the areas properly. Okay, so having drawn this, the next thing is, first we'll find delta B, theta B, then delta C, theta C. Okay, so only this quantity first, theta B at this portion. Okay, first, so we'll use the first theorem, So theta B is equal to area of M over EI diagram between A to B. Between A to B. That means you have to consider all of this, all the three diagrams. Okay, so first let's start with this. So I've marked this first. 1, area of a triangle. So half into base 2 meter, height 20 over EI. Similarly, second, so it's a rectangle. Area of a rectangle 20 over EI into 4. So this is second quantity. And third, half into base 4 into height 80 over EI. So again, 80 over EI you can write it here only, or EI you can take common. Both will be same. So after this, we'll go on simplifying. See, there is a reason why you have to simplify this here, write it here, and third quantity. Why I'm telling you all to write this here only is because, so first triangle area is 20 over EI. You can write it here. So this step is very important because these are the areas of all the three quantities, and you can write it here itself. So that's how, don't skip out this step. Things become easy. Otherwise, unnecessarily, again, you have to use this area, half into base into height, and solve this. So write this 1, 2, and 3, and this is theta B. And because it's a rotation, answer is positive. It is measured in radians. So answer is positive. That means it is a clockwise rotation. Similarly, after this theta B, we'll find delta B. So this should be in a sequence because this is the area, moment of area. If you find out this area, if you multiply for this area, if you multiply the CG distance, then this will give you delta B. Okay, so now next find out delta B. So delta B is nothing but deflection. That means this vertical deflection. So it is nothing but first moment of area of M over EI diagram. It means moment of area diagram, area of M over EI diagram. That means area into its CG distance. Area, CG distance. Okay. Now it is important to find out about which point. Now because you're finding this delta B, you have to find this M over EI diagram, that is CG, about B point. Whichever point or whichever deflection point you're finding, you have to find moment about that point itself. So now this is delta B. So finding M over EI diagram across about point B itself. Okay. So now just check this out. So this is first area into its CG distance. We have already found out, we have marked here 1, 2 and 3. So we'll follow the sequence. So first is the area of a triangle. So area of a triangle I've already found out here. So I'm taking this value directly here. So this is the area. Next, CG distance. We're finding about B point. So CG distance across B about this point is, again, area of a triangle measured from the apex. So apex is 2/3. This is 2/3 and this distance is 2 meter. So 2/3 of 2. Likewise, second area of a rectangle. So area of rectangle we have already found out here. We'll write down this value 80 over EI. So this is area of rectangle. So CG of this rectangle only is 4 divided by 2. This 2 meter. But you are finding about B point because we're finding delta B. So you have to find moment about V. So you have to add plus 2 for this. So it's 4 divided by 2 plus 2. Next, third quantity, that is area of a triangle. So area of a triangle is, we've already found out here. So this is the area of a triangle. I've written it here. Next, again, centroid of this is at this point. Then centroid of a rectangle measured from the apex. You have to measure it like this because point B is here. Measure it like this. So it is 2/3 of base. So 2/3 of 4 plus 2 meter. Okay. So when you solve this, you'll get delta B. So delta B, again, the answer is positive. That means deflection is downward. So these are the two end points, that is theta B and delta B. Similarly, you have to find out this, that is theta C and delta C. So again, how to identify this? Here, they have just asked slope and deflection. Every loaded beam at every point, wherever there is a load acting, it undergoes rotation as well as deflection. In the previous problems, if you have noticed, they had specifically asked you to find deflection and rotation at the free end, or they specified the point and it had to be the free end. But here they have not specified any point, so it is understood that you have to find both at both the points. Okay, now let us find theta C first. So theta C is nothing but, again, area of M over EI diagram. Now pay attention. See here, this is theta C, area of M over EI diagram between AC. See, it is at C point. So in AC, you have to take only the AC span. So in AC span, if you check it out, there is only rectangle and a triangle. So you have to consider only rectangle, that is second quantity, third quantity. We have marked here second and third because we are finding only at AC. In AC span, there are only two areas. Okay. So area of M over EI diagram between A and C. So there are only two areas here. So because there are only two areas, what you can do here is area of this plus area of this. Okay. So area of the second quantity, we already know, is 80. Next, area of the third quantity is 160. So when you add both of this, so it is 240. 160 plus 80, that is 240 over EI. Now you can check this out. What I have done here is I have taken trapezium, area of a trapezium. If you take area of a trapezium also, you get the same answer. Or if you split that is area of a triangle and rectangle, you get the same answer. But things are simple if you just split them into a rectangle and a triangle. Okay, so this is 240 or EI. Next, the same thing. Now, if you want to find delta C, so delta C is first moment of area of M over EI diagram about, now this is important, about point C, because here I've written here delta C. Delta C means you have to find moments about C point. That's why it is C here. So again, as usual, so it's the first quantity. You can check this out. First, rectangle. Area of a rectangle, 80. 80 over EI. Then what is the CG of this? Only this triangle about C now. So it is 4 divided by 2. So it's 4 divided by 2. Next, plus. Third quantity, it's a triangle. Third quantity is 160. So 160 over EI. Okay, 160 over EI. Then CG. CG of this triangle, CG of this triangle about C point. So about C is 2/3 of the base. So 2/3 of base, that is 4 meter. So that's just 2/3 of 4 meter. So when you solve this, you'll get the answer 586.67. Now you can just cross verify here. Theta B, rotation is more than theta C. So theta B is almost 360. So theta B is 360, whereas theta C is 240. Theta C is lesser, theta B is more because it's a free end. Similarly, delta B is 1093 vertical deflection. You can see here. This is 1093 and it is always in meter. 1093 and delta C is just 586. 586. So here it is maximum, here it is less. Okay, this is how you solve the problem. Again, the main thing of moment area method is, first if you want to find theta, find area of M over EI diagram. Next, if you want to find delta, that is deflection, it is area into its CG distance. That's all. All right. Next, the third type is, you just check this, find the maximum slope and deflection for a cantilever beam L subjected to a couple M at the free end. So it's a simple cantilever beam AB with a length L, and at the end, free end, there is a moment. The end, there is a moment M, and the moment is clockwise moment. All right. So again, as usual, first draw the deflected shape of the beam. So it is a fixed support. So up to certain length, it is straight, then it gets deflected. All right. So because it is A point, no rotation, no deflection, both are 0 here. Then this is the delta B, that is deflection at V. Then at theta B, just draw a line like this, tangent. Then this is marked as theta B. These are the two quantities you're supposed to find out. Now, as usual, first, after drawing the deflected shape of the beam, draw the M over EI diagram. Now see here, right side, again, right side clockwise is negative. So draw a straight line. So moment is acting at B. The same moment is carried forward to A. So it's a 0 line. So M is the ordinate here. Same thing, it will be here at this point. Then you have to join this back here. So M is the bending moment diagram basically, because there is only one moment. So because it is M over EI diagram, you have to just divide that M over EI. Divide this M over EI. Same thing, divide M over EI and show it in the negative side. Next, so we have to find theta B. So to find theta B, apply Moore's first theorem. So it is theta B minus theta A is equal to area of M over EI diagram between B and A. So area, so it's a rectangle. Area of rectangle, length into breadth. So L into M over EI. So since theta A is 0, because no rotation is happening there, so theta B is equal to M, that is ML, M into L over EI. So again, area can never be negative. So just ignore this, and it is ML over EI. So this is at the free end. Next, delta B, delta max or delta B, apply Moore's second theorem. So second theorem is again half of, now see here, this is a rectangle. Area of rectangle you have already found out here. That is ML over ML over EI is the area. Okay, this is the area. Then C area, theta delta B is nothing but area into CG distance. So area is ML over EI is the area into CG. Exactly half of L. Half of L is L by 2. So it is ML square over 2 EI. So delta max is, or delta max or delta B is ml square over EI at the free end.